be discussing the problem number 5 of INChO 2002, and let's just dig totally into the problem. So this particular problem, it comes in three parts: 5.1, 5.2, and 5.3. So let's just go and watch what happens. So in this particular problem, the problem number 5.1, it has been told to us that a particular hexa-aqua complex of copper that has lambda max as given, it reacts with I minus and and forms a colorless CuI, and this particular compound and iodine is being liberated, and a particular reaction which goes by is being depicted as follows. So it would ask a couple of questions. Like it has been told that consider the dissolution of iodine into Ki. Then we have to assign which is the acidic and which is the basic species. Secondly, we have to formulate a given equation of the liberated iodine reacting with Na2H2O3, which is being given externally, and we have to supply the equation for this reaction as well. In the balanced reaction 1, this particular reaction here, so we have to say which species is being oxidized to what. And secondly, we have to, as per the VSEPR theory, we have to give the structure of I3 minus. Then we have to give comment on the geometry of CuH2 whole 6 and explain why CuI is colorless. And we have to also calculate the spin only magnetic moments of this particular complexes. And lastly, we have to find the crystal field splitting energy of CuH2 whole 6 given this particular data. So coming on to the solutions part, as in the first sub part, we had been asked that this particular iodine, which is being liberated from the equation 1, it is reacting with this excess Ki. This is excess, and it forms this K plus I3 minus, and we have to signify the acidic as well as basic species. So as you can all see that iodine is taking electrons from I minus, so obviously this would be an acid as per the Lewis concept, and similarly I minus is donating its electrons, so it would be considered as a base. Secondly, this liberated iodine, the iodine from equation 1, it's reacting with excess, not excess, it is being, the Na2O3 is being given externally, and this particular reaction, which is quite famous, so need not tell much about this. So this particular reaction happens. Secondly, this particular Na2H2O3, which is present here, it's getting oxidized to Na2S4O6, and secondly, what happens in that first reaction, we are getting I minus to I2. So these two reactions are happening in which oxidation happens, and the species which are being oxidized are Na2H2O3 and I minus respectively. Then we have the VSEPR model of I3 minus, which is quite similar to XZF2. We can see it like that. And this as let's just take one I minus to be xenon, and we would be leaving out with structures like this XZF2, right? So this I minus gets its noble gas configuration. It has 3 lone pairs which are arranged equatorially, and 2 iodine atoms which are on the axial positions, and we can comment on the shape by Vennt's rules. Okay, so the answer to why are these lone pairs present in the equatorial position and not in the axial position, this is being given by the Vennt's rule. We can apply that here. Then it's given that we have to basically comment on the shape of this hexa-aqua complex of copper. So as you can all see, this is the central metal atom, and it has 6 ligands. So obviously the coordination number would be 6, and the shape corresponding to this would be octahedral. But there would be a tetragonal distortion, and this particular thing, this tetragonal distortion term, it strikes to us in a particular concept known as John Teller distortion, which would be studying in detail in the further videos, so stay tuned for that. So let's just comment on the electronic configuration. As Cu plus 2 is being given, so it obviously it would be 3d9 and 4s0, and the orbitals that would be participating in this hybridization would be s and 2, with this D. So 1s, then we would be having 3p and 2d. So this would combine and would give us sp3d2. Again, CUI is colorless because obviously its configuration is CU plus, and it has this 3d10 and 4s0 configuration, and it's diamagnetic and doesn't impart color as because no unpaired electrons are present. And since no unpaired electrons are present, then there would be no DD transition. So again, I'm not telling that if there aren't any unpaired electrons, color won't be imparted, but there are other concepts as well, LMVT, charge transfer, and much higher concepts. But taking account into the ground level, if a particular complex doesn't have any lone pair, then it would be colorless, like getting a very direct, or like we can say this is as a mnemonic, more sort of. Then we have to calculate the spin only magnetic moment of CuS2 whole 6 plus 2. So this particular thing, like we can say term, it goes by the formula under root n times n plus 2, where n is equal to the number of unpaired electrons in the particular complex, which is 1 as we calculated at the starting very beginning. So diagnosing the values, we would be getting it root 3 Bohr magnetron. This is the unit of spin only magnetic moment. Then we have to calculate the crystal field splitting energy of CuS2 whole 6. So as we know that the energy goes by the formula Hc by lambda max, which had been supplied to us earlier in the question. So basically substituting all the values there, we will be getting 150 kilojoules. But the answer had been asked in this centimeter inverse form. So as we had provided with the data, 1 kilojoule is equal to 83 centimeter inverse. Putting this value here, we would be getting this particular value, which is our answer to part 1. So let's just dig into the part 2. And in this part 2, there is this aqua complex of copper again, this hexa aqua complex. And what is being done is that we are replacing the aqua ligands, that is aqua means water, and subsequently by ethylene diamine, which is a symmetrical bident ligand. And we would be getting this 3 complexes. Obviously what we are doing is that we are basically removing 2 water molecules and adding one EN molecule in place of that. So first 2 water molecules are removed, then 4, and subsequently all. So basically we have to give the IUPAC names of these particular complexes. And in the second phase, we have to comment on the various structures that are possible for this particular molecule, and we have to assign its configuration. So let's just proceed to the solutions. So first of all, as you can see that the Iupac name is like quite trivial, most of us know. Still, I would just, let's say, explain this one particular example. So this is of Cu S2O. Is that CuS2? Okay, so whole 4. Okay, CuS2 whole 4 En, and there is plus 2. So first of all, there would be this tetra aqua is because 4 water molecules are there. Then there is this ethylene diamine, which corresponds to En. Then we have to give the central metal atom along with its oxidation state and ion, as because this is a cation. So the other two are like quite trivial, we can attempt that as well. So like completely hopping to the structure of Cu En whole twice S2O whole twice, we have to like comment on this like compound structure, and we have to also assign configurations to this. So as you can see that this is like symmetrical bident ligand. So and this is a unident ligand, and 2 of them are there. So 2 into 2 plus 2 is equal to 6. So the coordination number of the central metal atom is 6, and this would correspond to octahedral state. So in this octahedral state, there could be 2 possibilities. Either these 2 ligands, this En ones, they lie in the trans position, or else they are in cis position. But if they are in trans position, there would be a particular POS, plane of symmetry, which would like dissect the molecule into equal halves. There would be, it won't be chiral. This is not chiral. Not chiral means this is not optically active, or you can say this is optically inactive. But in the second structure, in which this particular ENs, these are in the this position, this is optically active, and due to which no POS is present, obviously, because if it were present, then it won't be optically active, right? So since it is optically active, it can be like found in two forms, D and L forms, means the dextro and the levo rotatory. So this was about assigning the configuration. So let's just proceed to the 5.3, that is the last part of the question. So it has been told that there was this one green that just mark upon the colors. So because this would be important in solving the question on the later part. So there was this one green aqueous solution of nickel chloride, which contains this particular complex, hexa-aqua complex of nickel, and this complex on treatment with the reagent NaCN, it yields this particular compound which is yellow in color, while when reacted with this particular reagent, it produces a blue color of this particular compound. So in the first part, we have to comment on the geometries of the given species that were asked. And in the second part, we are told that the electronic spectrum of NiH2 whole 6, it shows a band at 8500 centimeter inverse due to DD transition. So it has been asked that where would one expect the transition for this particular complex. So the first part is quite obvious, but the second part needs a bit of understanding. Let me explain it as well. So it's told that this particular compound, it shows a band at this particular frequency, means that there is a like DD transition occurring at this particular frequency. So it's asked that where would the DD transition occur in this particular complex, as this whole complex with respect to the original complex, that is NiH2 whole 6, whose data is being given. So so we have to comment whether it would be 8500 centimeter inverse, more than that, less than that, likewise, right? So we can do it in two ways. One is to proceed a very technical, proceed technically, or else we can do one thing is that we can proceed it via a street smart method. What do you mean by this? Is that, as I told, that we have to go via the colors, right? The color would be very important in solving this particular question easily. So as you can see that there is this green color which corresponds to NiH2 whole 6, and this blue color, it corresponds to this particular complex, right? So as we all know that green in Vigor, it comes after blue, means that when you go from violet to red, there is an increase in lambda, but there is a decrease in frequency, right? So you can see that the frequency of green color is less than that of blue. Okay? The frequency of green color is less than that of blue. So when we are moving from green to blue, there is an increase in what? Increase in frequency, right? So it shows that this particular we can say complex, it shows a band at 85 centimeter inverse, but do not dare to make a mistake that there would be increase in frequency. Why? Because we should be having this particular knowledge that a particular compound, it shows the complementary of the color it is absorbing, and we can judge it by a color wheel. Let's say this corresponds to Vi, there are Vigor and indigo, then we have blue, then we have yellow, then we have green, then we have orange, and then we have red. What does this color wheel say is that if a particular compound is absorbing yellow color, so it would be giving out red color that is observed. So what we observe is that this particular compound is having a reddish appearance, but what is the reality, what is the ground reality, is that it is absorbing yellow color, due to which a red color is giving out. We can understand it like this, as Newton told that the summation of all the colors is a white. That white light is a we can say chromic combination of all the four colors, that is VIB, GYOR, Vigor. See, this particular complex, it absorbs yellow, means in the given light, like say we have a this box in which a particular complex is present. We are entering white light from the left hand, and we are observing the light which is coming out. So what happens in meanwhile is that this particular compound which is present in the box, it's absorbing this yellow light. So means that in the given outlet there won't be any yellow color. So what would this mean? That this given out color is equal to white minus yellow, and the summation of white or like white minus yellow is basically red, right? Which is also depicted by the color wheel, and we say that a particular compound appears complementary to the color it's absorbing, right? So obviously it is absorbing frequency of more frequency, so its transition should be at low frequency, means the answer should be 85,500 centimeter inverse, less than that, right? So let's just now proceed it technically, right? So as you can see, first of all, the geometry. So it's quite obvious, it's octahedral as the coordination number is 6. Then we can basically judge the geometry of this particular complex as well, as because its coordination number is 4, and secondly this Cn minus, this is a SFL, means that this is a strong field ligand. So what would it do, right? So for that we have to draw the electronic configuration first of Na plus 2, because its oxidation state is plus 2. So it would be 3d8 and 4s0. So 3d8 configuration basically depicts this: 1 2 3 4 5 6 7 and 8. So what is the role of this particular SFL? It is that it does the pairing of these two unpaired electrons and make them sit in one particular orbital, due to which there would be one vacant orbital left, which would be used in further, we can say, hybridization. Just say D, then there are 2s, and there is this P, DsP2, which would give us DsP2, which corresponds to the square planar state. Secondly, we have to draw the geometry of this particular compound. Let's just break it into two halves. It's basically an easy question, only the complexity is an issue. So as you can see that nickel here is bonded to 4 atoms, 4 chlorine atoms, so hence its coordination number is 2, and moreover it's further coordinated with this complex, we can say, groups, and 2 of them are there, hence the total coordination number would be 6 with respect to Cl. Let's just depict this particular group, that is the complex one, by C, the complex group. So there are this 4 chlorine which are attached to this nickel, and there are this 2 complex groups which are attached. So with respect to nickel, this is octahedral, but since it had been asked that we have to comment majorly on the geometry but not the individual geometry, just see the difference that we are speaking about the geometry with respect to nickel is octahedral. We have to use the word with respect, as because when we see with respect to this arsenic atom, it is we can say tetrahedral shape, and the official answer which was given was a tetrahedral. So there was this one ambiguity which I found in the solutions, and elsewise the we have to mention with respect to which atom, because the whole molecule is not octahedral. It's a mixture of octahedral with respect to some XYZ atoms, and with respect to other atoms it is, or it may be, tetrahedral or any other thing. So that was that, and coming on to the last part, whose answer we had already derived by using some street smart methods, but still if we desire to solve it technically, we can proceed this, but proceed technically also. Let's just do one thing, is that this nickel, this NiS2 whole 6, water is obviously a very strong, we can say, ligand as compared to Cl minus, and obviously this particular pH3AS, this is a cationic ligand, so this would have even more less tendency to give electrons. It would come more further in the spectrochemical series. So first of all, we should be having the knowledge of the spectrochemical series, so it would make us understand what happens basically when there is the formation of a particular complex. As you can all see that this NiS2 whole 6, it shows a band at 85,000 8,500 centimeter inverse due to DD transition, And since H2O is a relatively strong ligand as compared to either of them, as we discussed, and this can be done via the spectrochemical series also, then the bond would be observed less than that. So let's just understand why. So what happens in DD transition basically is that there are two d orbitals, say d1, and there is this d2, and this particular electron is being excited from d1 to d2. So there is this one particular gap that the electron needs to overcome, and the energy needed to overcome this is being given externally, and the energy, that the particular energy which we are supplying is this, and that this particular energy has a frequency of this 8500 centimeter. But what will happen is that when we are changing the ligands, then this particular gap would be affected. Obviously, the if we alter the surrounding of the particular complex, then the gap energy would decrease, and subsequently the energy needed would decrease, right? So let's just say we are using a strong field ligand. So what would happen is that it would diminish this energy level, so due to which the energy required this would go down. That means the frequency would go up. So when we are moving from water to this particular complex in which chlorine and a complex part are there, both of them are weak ligands, due to which the energy gap would go increase, due to which the frequency would go decrease, because the energy required to excite now is less, right? Hence the particular answer would be 8500 centimeter less. So either we can solve it technically or via the street smart method which I discussed earlier here. So two of them are like a very good methods, though I would be suggesting you to go via this first method because that's a more logical path of solving questions like this, or else we can get a feel or a gist of this particular solution via this technical aspect as well. So this was all for today. So we would be like summarizing the total thing is that in this problem number 5 of INChO, not much we can say advanced it is were there. We can mere solve it by the JEE knowledge. Though some parts like the tetragonal distortion and all, these were like the plus ones, and we have to see these plus ones because there are possibilities that INChO might ask questions upon this, because these terms are already given, or we can say these came previously, right? So we can expect questions from these as well, or else this particular problem didn't had like much complexities in it. So this was it. Thank you. That's all for today.